Welcome, my astro friends. I'm excited to have you here for our very first episode of Sky Tours. Quickly, some logistics. You will see a field for comment on the right-hand side. Please make good use of that. I'm multitasking, and when I get a chance, I will gladly address for comments or questions. Also, please do not forget to adjust your YouTube window to HD. You can do that at the settings wheel at the bottom right-hand side of the screen. Often it is on low resolution by default. So you should actually have seen a message I just said starting soon. You should be able to comment there. Okay. So I have launched the first telescope already to capture our first target in parallel to save some time. In a session we will target about 2 to 3 objects, and a session will last about 30 minutes in total. In general, the image takes about 300 seconds. It's a single image, it's a black and white image, and you will see it really raw from the telescope, which is exciting, of course. And a session will be announced ahead of time, and it'll be in general on the weekends. There are some exceptions for holidays and so on. And of course, your comments are most welcome. Any recommendations you may have, any wishes, please send them to us at Sky Tours. And in March and April, we will also include the planets because that's the time for Saturn and Jupiter. And of course, you will know from my Periscope that earlier I have often done the moon, and we will do the moon, of course, too, because it's exciting. So, let's get going. So, welcome to the heart of Australia, where it is about 3 a.m. local time and the kangaroos are still asleep. We are blessed with modern technology, where we can sit in a northern hemisphere. By the way, I'm in Vancouver at the moment, and it's snow outside. Can you believe it? And in fact, anyone else on Earth can tune in, and we can enjoy one of the finest and clearest skies on this Earth. A few months ago, I did visit Siding Spring in New South Wales, Australia for the first time, and I instantly loved it. Let me briefly share with you my experiences. So you should be able to see, that's iTelescope there. Yes, it's iTelescope. Hi, there's someone who's, Ankit said hi. Well, hi to you, good to have you. So have a look. You can see kangaroos jumping around. That was my very first experience. That's what happens on the grounds there. It's quite remarkable. And just as you go nearby into town, and it's a very isolated place, you can see wild parrots on a field, and they make a lot of noise. So I'm just going to show you that. Those are my impressions. And then, of course, well, the weather's not always perfect, and sometimes you have this incredible atmosphere. And you have this incredible atmosphere, and you see these crimson rosellas right in front. And it's really marvelous. You can so these are wild parrots, and you can see they even survive in these incredible winds, and they come and eat bird food. All that was enjoyable. And then, when it is harsh weather, I also had time to visit the dome. You just saw that in the first little movie. And that's a 4-meter telescope they have there. Those for professional astronomers. And it has an incredible mount, and they're very friendly to explain everything. And then finally, when the weather does clear up, you get this wonderful view. You can see a panoramic view on the top. You can see as far as the eye can reach for hundreds of miles across the horizon. Oh, I should say tens of miles, not hundreds, but tens of miles. I'm exaggerating a little bit, but it is an absolutely incredible view. And below then, you can see in the evening, the roof will open of iTelescope, and that's where you enjoy your clear skies. So it is absolutely incredible. And it takes a lot of energy because there's so much to do during the daytime, and then at night, when you finally, you have to have a lot of more energy for the nighttime. So there's always something to do. So anyway, time to step outside. Now let's go outside and have a quick look at what it actually looks like. And it's quite incredible. I took my camera out here and did a simple 5 to 30 second exposure, and look what you get. It's absolutely incredible. This is looking towards the southwest, and I used a wide angle lens there exposed, and you're looking straight into our own Milky Way, which is the galaxy where we're at home. This is our own home galaxy, and there are millions of stars we're staring at. Quite incredible to capture all this in just a few seconds. And there, just above the 4-meter dome, you can see the Southern Cross. So let me just get an arrow here to show you the Southern Cross. That's right here. That's where the Southern Cross is. And it's quite incredible too, because on the next image, this is as the sun goes on, it just gets deeper and denser, and the Milky Way, our own galaxy, stretches right up to the zenith. It's absolutely magnificent. It blew me over to see something like that. So, what is it then? What is so great about the southern sky? A famous astronomer, and we'll come across his name again in this session, he was called Bock from Harvard University, said, "All the good stuff is in the southern hemisphere." And I couldn't agree more. Why do I say that? Starting with the Southern Cross, which you just saw, we have an equivalent pointer in the north, and you may have heard of a polar star, you've seen it many times. And, well, the polar star or the North Star does exactly that, it points to the north. But that's about it for the naked eye. And it shows us the direction. So at latitude 49 degrees north in Vancouver, where I am, or in equivalent European cities such as Stuttgart and Paris, which is also on 49 latitude, we only look south. The Southern Cross, on the other hand, with its pointers, and I will just jump over and show you a better view of that. 1 second. This is a much better view. What I have done here is I've overlaid my image that I took earlier with a coordinate system of all the constellations, so you can enjoy them much better. And let me just move the arrow to the Southern Cross, which is right there. That's the Southern Cross. There you go. So it's just there. That's the Southern Cross, and it has pointers. I'm just going to show you the pointers that point towards the south, and that is Beta Centauri and Alpha Centauri. And the top star is one of the pointers of Alpha Centauri, and it's quite special because that star actually consists of 3 stars, one of which is called Proxima Centauri, which is the closest ally or the closest star we have to our own solar system. And it is just over 4 light years away. Okay, so there we are. And let's just take a further look up. And now we are looking already towards the zenith, and it is incredibly beautiful. And again, I've overlapped the coordinate system, so it's easier for you to orientate yourself. But this is something that we also see in the northern hemisphere. That is Antares. Antares is a big red giant. Okay, it's a huge, huge star. And we usually see it at lower horizons. If you're in Hawaii at 29 degrees north, you'll see it a lot higher. And then as we move more and more upwards, we come to the heart of our own galaxy, and that is the famous Sagittarius of our galaxy, Sagittarius. It's absolutely magnificent. And think about this. This was just a 5 to 30 second exposure. that I took, and you get these incredible results. It's mind-blowing what we can do. And I'm using this as an overview to let you feel at home where we actually are in Australia and what you see when you go outside. And this is really what you see. So right here is a tiny yellow dot. A tiny yellow dot. I'm just moving the arrow there now. And that tiny yellow dot is what we call the galactic center. That is the center of our Milky Way. That's where a huge, huge black hole lures in the center, and that keeps the whole Milky Way alive. Okay. Now, having said that, let's go and jump to our first object. So, let me just jump back again and give you an overview. That's what I wanted to show you. Here we go. So this is again my image, and we have three objects for today. The first one is called the Coalsack Nebula, which is sort of a darkish patch that you typically see when you look up at the Milky Way in Australia, or in fact anywhere on the southern hemisphere. And you can also just about see this when you're in Hawaii, but only really the Southern Cross can only be seen just above the horizon from Mauna Kea in Hawaii. And so we're going to see that today, and then there's another object called the Running Chicken Nebula, and then there's a third one, and that's a galaxy leaving our own Milky Way now, and that's called M83. Those are the ones we're going to visit. So let's get going. So let me just jump back now and go to the telescopes. And in fact, I've just got the first result here, and I ran that in parallel. And let me just see if I can get the next one going, if we're not offline. Let's see. I'm just launching this for our next target, just to save some time. Let's see. I will do that. Acquire image. There we go. It's running successful. So you can see this is in real time. So I'm jumping back to the first image now, and there, this is quite interesting. Let me just see. So what we're looking here at is at a very, very dark patch of the sky, and that's called, this is right there where, that I showed you, it's right there where the Southern Cross is. Okay, and typically you can see this with your naked eye, and you can also see this with binoculars, and it's typically about 5 to 7 degrees wide. So that's why we take a wide-angle telescope for this. So it's strikingly dark, even for the naked eye. So what looks like dark dust actually is a lot of dust consisting of thousands of solar masses. A solar mass is the mass of our sun. It's very, very heavy. So it consists of thousands of solar masses of gas and cold dust grains, which scatter light out of our field of view, and that's why it appears so black. And it's about this whole distance that you see right across there is about 50 light years. So it's a vast, vast, vast area. And the distance, I should mention that quickly. Let me just jump to this. This is the distance, okay? So this is in the constellation of the Cross, as I just said, and the distance is about 600 light years. That's where we're traveling now, 600 light years into our own galaxy. So let's just jump back to the picture again. So then what is so special about dark dust? Well, dark clouds consist of sub-micrometer sized dust particles coated with frozen carbon monoxide and nitrogen, which effectively block the passage of light at visible wavelengths. So that's the wavelengths that we see. They are transparent in the infrared, which we cannot see. Also present are molecular hydrogen, and hydrogen, you probably know, is the most abundant element, the most elementary abundant element in the universe. And there's also some atomic helium and CO chains, as well as ammonia in there. But now comes the interesting thing, light. And by the way, the star that you see on the right, that is Alpha Centauri. That's this bright star that you see on the right, that is Alpha Centauri. It is not part of the Coalsack, it is just happens to be there at the same spot. So it is, as I mentioned before, the closest of Alpha Centauri is Proxima Centauri, and that's 4 light years away, whilst this object is actually 600 light years, which means light takes 600 years for us to reach. So the perspective is different there. But what is interesting is that light that actually does penetrate, and it's not completely dark, nothing is completely dark, there's always some light somewhere coming out. This light looks very similar to the light that we have in the sky. During the day we have a blue sky, and in the evening we have a red sky. And I mentioned before, these are sub-micrometer particles. So what happens actually is they are very, very good at scattering. They're called Rayleigh scattering, named after a very famous Englishman called Lord Rayleigh. And that's what causes light scattering, because blue is very, very effective at scattering light, red not so. So there's a lot of infrared, dark red coming through there. So it isn't basically this dark cloud is a filter. And what is also interesting is right in the center, and let me get my arrow back here, right in the center we have an open cluster. It's an open star cluster. Oops, I must just make my cursor move. Sorry about that. Here we go. We have an open star cluster, and that is, young star clusters are always associated with lots of dust, because that is how they are born. Without all these dark patches of dust, we will have no stars, and they're essential for the life, for new life and new birth in a galaxy. So that ends the first that ends the first object, and let's just have a look now. Let me just get the arrow out of the way. 1 second. Let's see. There we go. That's better. So let's see what our second. Let's see how far we've come here. Let's see now. Get my preview for the next image. That's building up. Oh, it's still not quite ready. Let me just check 1 second. It's still working. It's still working. It's still working. Well, that's good. That's the way it is. So we just have to be patient now. If you have any questions, I'm reading, so just go ahead and ask. But the telescope is ticking away. But I will, however, in the meantime, make you acquainted with our next object. Let me just get my cursor back. There we go. There we go. That's our next object. So we are now flying towards the Running Chicken Nebula, which is a curious name. So this is in the constellation of Centaurus. As you could see, that was also in the Milky Way. We could see that. And the distance is a lot further, so we're traveling a factor of 10 now. This is 6,000 light years away. And I'm just looking and waiting for the telescope to acquire the image. So let's just pause a little bit. There we go. We're making all this in good time. You can see this is real time, by the way. This is the interface that we're using. It's similar to when you drive a car. You don't need to know about the engine. You need to know nothing about the engine. All you need interested is to acquire images. So I'll just show you how we do that. If I click here on, if I know nothing, it's just like a new driver, I have this column called a one-click image. And it's quite fantastic because you can see that's a live image of our Milky Way, just the one that I was just describing. And you have all these objects there, and all you need to do is just click on one, and the rest will happen by itself. So in this case, you'll get black and white images. It's just a single image, and they're typically 5-minute exposures, which is 300 seconds. So that's all there is. And then it gets more and more advanced for the advanced users. There are also many researchers and so on. So they'll do all that. And then I have this wonderful thing called preview image. It's quite simple to use, but I'm going to look at the system status and see if our telescope is finished, and it looks like it. So we may just be, let's click on preview last image. Let me just press refresh. Let's see. It's still thinking a bit. Brad's there. Hi, very good. Would be interesting to view the dark nebula in infrared. Yes, it would. And it's, it's a very interesting point, Bart. We have, actually at iTelescope, we have one telescope that can look into the near infrared. It's quite remarkable. So that can look just above, here it comes. That's wonderful. Just give it a little bit time to load and we'll be there. There we go, fantastic. Now this is quite amusing. So this is the running chicken nebula. It's an emission nebula, so it's very, very different. Now you'll ask yourself, what is a running chicken here? Now you have to use your imagination. This looks somewhat, and I may be wrong here, this looks to me somewhat like a head, an eye, a mouth, and this looks like the wings, and I believe those are the feet. Now you need a lot of imagination for this, and others may say, well, the chicken looks a bit different, but that's what it is like. This intense radiation in turn excites the surrounding hydrogen clouds, making it glow a distinctive shade of red, and I'll just now show you what that means. Okay, yes it is streaming live. We are, Danny, we are streaming very much live. Yes, we are. And I can see your comments, so if you have any comments, feel free to comment. Okay, so that raises an interesting question, Does it make sense? Ultraviolet is something we cannot see, and it's very energetic, and yes, yet I'm saying that this is actually, which at the moment appears like a black and white image, is mainly reddish. So where does that come from? Because, for example, if you light a fire, or if you look at a star, you would expect something yellow. So the first reaction would be, well, why isn't it just shining bright yellow, or like coal does, it just glows? Why are the images black and white? That's a good question, Robert. I'll just address that. It is common for telescopes because when we look at the sky, the beautiful red that you see, our eyes are not very sensitive to that. And astronomers are interested in a much, much wider scope. And these glorious pictures that are made of these beautiful colors, which I will show you in a moment, are compositions of what we call red, green, and blue. It's the same way a digital camera works. It's RGB. Your camera doesn't really take a color picture. It sort of integrates over the different colors and uses different filters. So that composition is usually done later. Okay, so that is done in post-processing. There are, however, single image color cameras, but they often don't look as spectacular as the images that you are about to see. I hope that answers your question. Okay, so let's get back to the question, and I will show you, I think you deserve this at the moment, to see something in color. Okay, so I'm going to show you something incredible in color now, because this is actually what a composite color looks like of the running chicken nebula, done by an incredible person who is called Josep Drudis, and he uses our telescopes a lot, so it shows you what you can really do. CCDs inherently take monotone pictures. Yes, you need to take multiple images. That is exactly right, Radix. That's a good comment. That's exactly what it is, and this is exactly what Joseph has done here. And I just wanted to thereby bring in the color image now to show you that, to explain much more what we mean about the colors. So where does the red light come from? Well, I was just talking about ultraviolet light coming from the background stars, and you can see these bright stars there, young stars feeding this emission nebula, feeding this emission nebula with incredible UV light, which we cannot even see. And what happens then is this light. One second. Stream is down. I'll be back. Okay, are we back now? I hope we are back. Sorry about that, the stream was down. Okay, back up. Thank you. Thanks for letting me know. No idea why the stream suddenly interrupted, but we're back. Okay, sorry about that, my friends. That's what real. You can see that this is very much live. Okay, so let's get back. Stream is back. Wonderful. Thanks, EB. Thanks, Andy. Good. Okay, so we're back. So what I was saying, and I don't know exactly where I lost you, but is what you see here is a result of a hydrogen emission line, and we call these the Balmer series. It is basically when ionized hydrogen recombines, the electron goes from a higher state back to the ground state. It sort of cascades down like going down a staircase, okay? So by jumping from energy level 3 downwards, it emits very red light, and that's what we're seeing here. And that's what makes these beautiful emission nebulas, and they are so popular. And you can see with so-called narrowband technology, which they use, which are very, very narrow filters. That's what Josep did in this case. You get this. Okay, so much about this. But there's one peculiar thing that I did want to show you. And let me point my arrow here. Do you see these black patches here? Okay, and I mentioned the gentleman called Bock, who said something about, which iTelescope are you using, says Rolf, and what is the focal length of monochrom images? Okay, very good. I will tell you, for this one, I'm using the telescope called T8. I think it has an aperture of about 10 centimeters, if I remember correctly. It's a refractor, and I think it is f4 or f3. I don't remember quite. Longer focal length, about 2.5 to 3 meter focal length, and that will allow us to really pop into the universe. It's called what we call a deep sky telescope. Okay, so for this one we're using a wide field. This picture was not done with wide field. This one was done with a much bigger telescope, but the initial image that I showed you was done with a wide field. If you want to really go in like this, we're using a 0.5 meter telescope. Typically we use T27, T30 or T31 for this, with all its color filters. I hope that explains it. Celestron, no, it's neither Celestron nor Orion, it's none of them. It's also not Meade. We use Planewave, mainly Planewaves, okay? Planewave is a company in California. They have a fantastic telescope house where they build these things, okay? So, anyway, let me explain quickly this funny dust particle that you see there. That is not a small dust particle. Thank you for the answer, you're welcome. Yes, Takahashi, that's also, thank you, Aaron. I meant to say not everything is plane wave. The refractor is a Takahashi. That's the right thing. So the big ones are the plane wave, the refractors are Takahashis. That's it. Thanks. Yes, and what looks like dust on our lens is actually not dust on our lens. Those are huge clouds in the emission nebula, and they are the birth. Those are the birth factories for new stars. So all these dark patches are really important for, well, you could call it recycling, death and birth of new stars. Okay, well, let's jump to the final image, and let's see where we are. 1 second. We're still doing quite well in time. Actually, with all the stream interruption, let me see. Where are we? Let me just get my arrow out of the way. I'm now launching T27 with M83, okay? So this is the third target. So I'm just going to launch that. 1 second. Let me just launch this and say acquire image. Oops, we're kicked out here. 1 second. Then it's no problem. We have another one. We are going to T30. Just hang on. There's another telescope here. There we go. I think that's also the one I was meant to use. This is the one. Sorry, acquire image. Oops, and it's another, we're kicked out there. However, I have been very cautious. If I still see this correctly, we should, we should be able to, yes, there it is, there it is. Because I'm multitasking like crazy, we are lucky, my friends, because what I did here is I just launched this on time. I was just told I can use T27, but it is exactly the same way I have done this in parallel. So just my image is there before it was kicked out, and we are now at M83, and I quickly want to just show you how we got there, okay? So we were now going far, far away. In fact, 15 million light years. So we leave our own galaxy, and we leave our own local group, in fact, and we have gone to another galaxy in the constellation of Hydra, and it's called the Southern Pinwheel galaxy. It's absolutely incredible. So this image has just been taken. So I've been multitasking actually, just before I was just kicked out. So you can see how keen our users are. As soon as they see a slot, they'll jump in. So it's all good. But anyway, what is interesting, let me just jump back. So this galaxy, let me jump back to the picture, in fact. Let me just get a close-up of this. There we go. That's much better. That's much better. Here you can see a close-up of M83, picture that we've just taken. You can see how beautiful this comes out. This is a 5-minute exposure with T30, one of the big telescopes we have. And what is incredible about this galaxy, look at the center. It's called a barred spiral galaxy. So why is it called barred? I'm just going to get my arrow again so I can show you this. It's called barred because and our own galaxy looks very, very similar. It's got a bar of stars right in the center, and these stars are mainly, this is the region where a lot of new stars are born. Basically, this bar acts like a gas channel, drawing gas from outwards, inwards, and this gas is a lot of hydrogen gas and so on, which is essential for building new stars. What is also remarkable, you can see all these clusters. These are clusters there, clusters of stars that are all birth factories. They're huge emission nebula. There are a few thousand such clusters in M83, the Southern Pinwheel galaxy. It's absolutely beautiful because we're looking at it face on, and it looks very similar to our own Milky Way, only it is about 40% smaller. You wouldn't think so. We are about 100,000 light years across from one spiral arm to the other, and this is about 40,000 light years across. So it's 40% only of that. But it's a very, very, very active. It's a very, very active galaxy. This was how the act was not in 1967. Well, it depends. You're right. I must have missed the question, but if it's 50 light years, you just subtract that, and that's when the light started. Yeah, that's right. But this is, of course, very far. This galaxy here is 15 million light years away. So that's the amount of time that it took for light to come all the way to Earth. It is so it's 40,000 light years wide, but it is, if I remember correctly, 15 million light years away. So again, I just want to show you also a color. Okay. Just give me a quick signal if you can hear me again. I restarted I restarted my software. I apologize. Computers are not perfect. Stream is back, upcoming now, says Aaron. Thank you. I apologize. I really do my best, but I was moving the arrow and suddenly my software crashed. Well, that's life. But you can see this is all in very good real time. So anyway, this is fine because I quickly wanted to show you the color image that was done by Josep, and you can see these red regions there, and those are all very, very active regions for new star birth. And that really concludes the session. There's one more thing I wanted to say, and it's better actually to see this in black and white, because sometimes a black and white image is just better than a color image. And looking right at the center of the galaxy, you will notice, if you look very carefully, that that white part, which is really the birth or the most important part of a galaxy, is off-center. It's about 200 light years off-center. It's like the dot's not quite in the middle. The reason for that is suggested that this must have been a collision between a satellite galaxy, for example, the Large Magellanean Cloud, which we also have on the southern sky, and the Pinwheel galaxy. So some satellite galaxy must have collided with it, and the Pinwheel galaxy basically absorbed it. It still has one big black hole in the middle, but the light center is shifted by about 200 light years upwards, okay? So that small shift is actually a large distance, okay? So that, my friends, concludes my first session. I hope you enjoyed this, and apologies for the small technical issues. I think we resolved them nevertheless. So it would be wonderful to see you back. If you have any questions, please go ahead. Wobble, says Andy. From Abu Dhabi, my goodness. Is there a black hole? Yes, there is a black hole, Ankit. There is a black hole in the center of nearly every large galaxy, if not every large galaxy. That is known nowadays through measurements, very, very well known. Okay, that was excellent. Well, thank you, Insight Observatory. Wonderful to have you on board, my friends. I really enjoyed that, and I hope you had a little bit of local feeling what wonderful Australia has to offer. I will go back this year too, and I will also be doing 1 or 2 live sessions from there as we progress through the months that will come. So thank you very much for being here, and if you have any further questions, let me know. We've been about 40 minutes, so I think I've taken enough of your time. So I wish you a wonderful weekend, or wherever you are. Nice greetings and guten Tag von Hamburg. That's great. Greetings from Hamburg. I'm glad you're all there. Very, very glad you found it interesting. Please tell your friends. Please subscribe. As you can see, we are asking $5 per month, and I think that is really quite generous. We're doing this out of passion. It would be wonderful to have you for our next tour. We will prepare this. We will roll out the whole plan. Thank you so much. I see all your kind comments. Really appreciate that. Hope you enjoy the enthusiasm and passion we all have at iTelescope. We love the sky, and we love having you here. So thank you for all that, my friends. Thank you. Take care and goodbye. Oh, there's one more question. At the top of the current image, there is a white line. What is it? Let me see. Of the current image, I'm just looking. A white line. I'm not sure. Oh, greetings from Washington State. I'm not sure. Let me jump back to the other picture. I'm not sure what you are referring to. Was it this one? Because that was the initial one. I know this is difficult to... Oh, you're welcome, Brad. Welcome, everyone. I'm not sure which image you are referring to, and I know it's a little bit difficult in the chat to describe that. The black and white image. Okay, well, there were several ones that I showed. I just have to make sure I find the one that you saw. You mean this? Now, I'm going to try and take my arrow back, but this arrow is precarious because it might crash the software, so let's take a risk. This is how I crashed it. I'm not sure. Do you mean this line? Hang on. It's very, very difficult to do this interactively, so I apologize. But maybe you mean this line. I'm not quite sure. Sometimes you see vertical lines, and they are from overexposed stars. When they overexpose, the pixels, sort of the light bucket gets overfilled and sort of makes a vertical streak. Maybe that's what you mean. Could be meteor flying by. Yeah, we see many, many meteorites. It's very, very typical, right? It's very typical. Looks like a cosmic ray. And it's very possible. I mean, there are all kinds of course, we have satellites. Satellites are the most common streaks that you find, but some are also made by the camera. This is very typical. Even if you look at Hubble images, the original Hubble images look absolutely disgraceful, you could say, because they're full of lines, and then they fix them. After 30 minutes, I finally found out how to comment. Thanks. Well, that's great, JK. So on that note, I wish you a wonderful Sunday wherever you may be. Some of you are already on Monday. And please tell your friends, sign up. Aaron, who's hosting you with the newsletters, will roll out the whole plan and we'll let you know. We'd love to continue and have you on board. Thank you very much.